Well, good morning, everyone. This is Larry Wilkins with the ABA Engineering Academy, and we're sort of working here with fourth stream backup equipment. We had some failures this morning on the Zoom equipment we were using, so I apologize for the way the video looked, especially on me, and the rest of them look okay, with the exception of John George, but he always looks that way. But we want to welcome you to our November edition of the engineering webinar. Uh, this is produced by the ABA Engineering Services with the Alabama Broadcast Association, and it's actually underwritten by the good folks at Max Connect. We encourage you to go to their website at maxconnect.com and look at all the equipment that they have and the services that they offer, especially the Max Connect remote unit that uses a dedicated Wi-Fi connection that you can use on your remotes or backup STL. So make sure you visit them at your leisure, matchconnect.com. I want to bring in, first of all, this morning, our co-host, John George. And John, I guess over in your place, it's like it is over here. We had to get up and put another log on the fire this morning.
We definitely did the same here, and it's going to be even colder the rest of the week. And up in the mountains of South Carolina, North Carolina, Tennessee, and Georgia, they had snowfall earlier in the week. So I guess you say we went from summer to winter.
You had some information you wanted to share with all the people that's on before we actually get into the program about the latest in EAS rules that was just enacted. Well, actually goes into effect, I think, sometime in December.
Yes, exactly. We always seem to be talking about EAS, and this is perfect with having Wayne with us today. But the commission is now going to require that stations have to use CAP protocol, which is your Common Alerting Protocol System in your EAS box, to be the lead for any alerts that go out. Now, the first thing a lot of people say, well, how am I going to do that? I don't have an operator at my station. Well, the major manufacturers, Sage and DASDAC, will be updating software as soon as possible, and that will allow the box to listen for the CAP protocol of the alert, and then if they don't get the CAP, it will immediately put on the audio alert from the LP1 and 2. They're doing this because the FCC realizes that the daisy chain, in a lot of cases, the audio gets distorted, is not the cleanest by the time it gets to the end of the link in a particular state, and at least the CAP does allow for much cleaner audio. It also allows for additional information to be distributed both to television and radio and the cable system. So this is something you should be on the lookout. There'll be a year to update your boxes and adopt the new CAP requirements. Also, coming along in the very near future is going to be a requirement that all boxes are certified, so that you are assuring the FCC and EAS that everything is protected behind a firewall, and you've had no breaches of or intrusion into your network that could affect the operation of EAS. So that's something to be on the lookout in the next few weeks as that goes into effect for the CAP changes in December. And Larry, it's back to you.
Yeah, I think the proposed rulemaking actually goes into effect because it was in the Federal Register December, I want to say 21st or something. I don't remember.
I think that is correct.
But the effective date that you have to have the service, your equipment upgraded, is December of 2023. So you have a year to get this, because it's going to take a little while for the manufacturers to get their firmware. I had a discussion with Harold Price with Sage, and also with the folks out of DASDAC. And I think DASDAC already has something similar in their unit, but there may be some changes. But the others will have to get the firmware out to the stations to upgrade that. So, as John said, keep a watch on that. Well, let's get to our program this morning. There's hardly any station around that you visit that doesn't have something in using digital audio or digital video. And we've come a long way in being able to digitize analog audio and video, and it's working very well. And now we've actually getting pretty well about being able to transmit audio from point A to point B, but there's a lot of stuff that goes on to get it from where it originates to where it's supposed to go. And I asked my good friend Wayne Pecena if he would be with us today. Wayne is the director of IT and handles broadcast operations as well out at Texas A&M in University in Texas. And there is a protocol called RTP, which is really heavily used both in radio and television, that has to do with the transportation of these packets from one place to another. So Wayne, welcome to the program, and we'll turn the program over to you now.
Well, thank you, Larry, and good morning to everyone for joining us. I'll get my screen set up here and get started. One little correction there, Larry. It's Texas A&M University, not those other guys 100 or so miles west of here. Well, anyway,
how's their team doing? No pun intended.
Well, they're probably doing better than A&M. I have no clue how they're doing, but I can just about assure you they're doing better than A&M is this year. We really don't want to talk about football. All right, let's get going here. As Larry mentioned, we want to talk about RTP and maybe a little bit of background of how we got here. I have a series of articles that is being published in Radio World magazine entitled IT for Radio Engineers. And one of the past articles was on RTP. And I guess that must have caught Larry's eye, and that's what brought us here. I can't miss, an opportunity for a shameless plug for SBE. These series of articles that are running really are associated with a webinar series that I did that was entitled CBNT and CBNE study topic. So each of the articles sort of picked a topic from one of those webinars, and that kind of became the basis. And of course, there's that 8 webinar series that is available to you on demand. So that's it for my shameless plug here. Let's talk about RTP. And well, what is it? Well, it is a IP network standard for the transport of real-time data. And in our broadcast world, that real-time data is basically audio and video streams. Now, RTP does have use outside, let's say, the media or the broadcast industry, particularly in automations, real-time control systems and automation systems. That real-time data in that case might be some type of process metrics or some type of information associated with some manufacturing process. But regardless, we're focused on what we're doing with it in the media and the broadcast world. As a IP network standard, RTP is going to be based upon a RFC. Actually, there's a couple of RFCs, 3550 and 3551, that really define all of the attributes and how RTP works. And of course, this is these are updated versions from the original ones back several years ago. So what does RTP do for us? Well, it does several things that is beneficial to our real-time media or that we are transporting. We can use it to reassemble out of order packets. In general, it can reduce latency and jitter with some buffering. And of course, it supports multicast. It's also important probably to note that what RTP is not, mainly or most importantly, it does not provide any type of quality of service. However, it does provide some performance information that might be used in quality of service applications. And also it does not do any type of resource allocation or reservation of resources. So where do we use RTP? Well, gosh, it is used in a lot of applications, such as voice over IP, applications or systems that are based on the AES 67, which then integrates pretty much with all of the audio over IP systems that are on the market today, whether it's Dante or Livewire or WheatNet. And of course, in the television world, SMPTE 2110 utilizes AES 67. And with that, the family of products is pretty broad. And of course, this is really not in the scope of our discussion today, but web conferencing systems that we're all familiar with, such as Microsoft Teams, WebEx, and certainly Zoom that we're using today rely on RTP. Although I should note that Zoom really is using sort of I'll call it a modified version of RTP. In other words, a modified version of that IETF standard. So with RTP, what are we really trying to fix? Well, this is the ideal situation where we want to send real-time information from a sender or a transmitter to a receiver. And with that, that sender is going to generate packets, in this case, RTP PDUs, and of course the PDU is a packet at some fixed interval. And ideally, in the ideal network, those packets are going to arrive in the same uniform pattern that they were sent. Of course, there will be some delay. That is the natural part of any network. And for clarity and illustration purposes, I've used some pretty large latency, because most networks you don't see a second of latency that I've used in my illustration here, but I've done that really just for clarity. Again, this is the ideal situation. And of course, I think we all know the ideal situation rarely exists anywhere. So in reality, we have something that looks like this. We have, of course, the sender is still sending those packets of real-time information, whether it's audio, video, or whatever it may be, at that repetitive rate. But over on the receive side, we see something a little different that happens. We see additional delays that may come into place. We see those packets arriving at different times throughout this session that's illustrated here with basically 6 packets of information. We, of course, still have our network delay or the latency. Some of that is natural, but there's also some significant delays that occur. And also we have jitter. Jitter simply is the difference in the rate or the time that those packets are received. And you can see different packets have different jitter values associated with it, as well as a situation where packets might arrive out of sequence or out of order that they were sent. In this case, packet number 4 arrives before packet number 3. So this is the real world that we want to fix. As a little bit of review, to maybe understand where RTP fits in the IP world, we have to go rely on our friend, the OSI model. And of course, the first 4 layers of the OSI model are considered the data flow layers. And this is where networking is focused. And of course, these should be very familiar to us, but the transport layer really is where we're going to concentrate. If we look at how a host device communicates with another host device across the network, we begin with some type of application that is going to generate what is often described as upper level data. That data then is passed to the transport layer where it is packaged in either a TCP or a UDP transport. With that, there's an appropriate header. That header and payload is then handed off to the network layer where it is encapsulated and an IP header added, which in turn is passed off to the data link layer with for practical purposes, an Ethernet header adder. And finally, we get down to the physical layer where those bits now are transmitted across the network. And of course, if we're going to encapsulate, we have to do the same thing in reverse for the receive side of things. And of course, at each layer of encapsulation, we have a different protocol data unit, or PDU. And as that information is sent through from the upper level application that is generating that across the network back through the de-encapsulation process, and ideally we're going to present that same data that was generated on the send side to the receive side. Again, today we want to focus on transport protocols, and there basically are two. There's the TCP, or Transmission Control Protocol, which is often described as a connection-focused protocol. Of course, as an IETF standard is designed or is defined under some RFCs. And then we have the UDP, or the User Datagram Protocol, which is a connectionist focused protocol, also of course defined under an RFC. And that brings us finally to the real-time protocol. A key thing to keep in mind about RTP is that it rides on top of UDP. It really is not a separate protocol. It is a protocol that sometimes it's described as a sublayer of UDP because it rides upon UDP. If we look at the difference, just a little bit of review between TCP and UDP, simply looking at the headers, you see significant difference. But keep in mind that UDP is used because it's fast. It's fast because it is simpler. There's less header information. That also implies there's less processing required or needed by either the send or the receive host, because there's simply less information there. It is considered, however, unreliable. And that term may not be quite, quite correct, because it maybe has the wrong and suggests the wrong meaning, but it's unreliable because there's no TCP handshake. In other words, TCP is considered reliable or guaranteed delivery because of the three-way handshake of send data, that data is acknowledged, send more data, that data is acknowledged. If that acknowledgement is not received, then the sender is going to resend that data. Also, of course, TCP has windowing features to optimize data transfer depending upon conditions. Well, no handshake, no windowing exists in UDP, but that's also one of the things that makes it fast and thus advantageous for delivery of our real-time media. So if we now take our basic OSI model and sort of simplify it and sort of tailor it to our multimedia type environment, you might find something like this. So again, particularly at the transport layer, we're going to have UDP with RTP riding on top of that. And of course, at the application level layer, we can have the applications that might generate that real-time data. And that might be some type of codec, whether it's audio only or maybe audio and video or whatever, that is actually generating the payload for the RTP. And in turn, we want to deliver that payload at the receive end to our receive host. So let's dig in just a little bit deeper into RTP. Again, of course, it's defined by an IETF RFC. RTP is designed for real-time media delivery. Already mentioned, it is often considered a sublayer of UDP in which it's delivered. And RTP is basically encapsulated in the UDP segments. Within the standard, there are 4 types of devices that are defined under the IETF RFC. We have the sender, receiver. Those I think are pretty obvious, but we also have the mixer and the translator. A mixer is simply a device, as the name might suggest, that combines RTP payload streams, whether that be audio or maybe video or whatever that media is. A translator is simply a device that is going to translate one stream into a different format. And often that is used in situations where in a multi host environment where maybe you have a sender or a receiver with less available bandwidth, and maybe that translator is used to create a lower bandwidth or lower resolution stream for that particular device. Again, keep in mind that RTP payload information is in turn, with its header, of course, encapsulated into a UDP session with its UDP header. That is in turn encapsulated in a IP packet. That IP packet payload plus the header is in turn encapsulated in a Ethernet frame. And of course, that frame as well as the payload is in turn translated to bits for transmission across our network. To dig even deeper, let's take a look at that header information, because this is probably really the key to understanding what RTP does and how it does it. The header, of course, consists of several fixed fields that exist. The first being a version. Currently, RTP is version 2, so that field will always be a 2. There's a couple of logical fields that have flags that may or may not be set. One for some padding. Padding is typically used when the payload that you're sending is not quite big enough, so to speak, and extra information or padding null packets are added to that. The extension header, once again, is a logical flag if there is an extension header used. The CC field simply is a count of the number of contributor source identifiers that are found. By default, this is going to be 1, but we'll talk about a situation where you may have more than 1 contributors, and simply this field is the number of contributors, and of course that can be up to 16 based on the standard. Another flag is the M, or the marker flag, and this simply is a significant event identifier. Well, what is a significant event identifier? it can be different things depending upon the application and the payload data. One example, it might be a marker to identify the start of a video frame, for instance, assuming, of course, our payload is video. We then have the payload type, the sequence number, and the timestamp, and I've highlighted those because we're going to talk about those in a little more detail, because for practical purposes, I think these three data fields are really kind of the key to RTP. Then we have a couple of source identifiers, beginning with the synchronization source identifier and the contributor source identifier. Now think back to that CC field, which indicates the number of those contributor source identifiers that we have, and we can have multiple contributor source identifiers if we have multiple sources of that multiple sources within our RTP stream. But again, we're going to focus on these three in a little more detail. Looking at the payload type, the payload type is a 7-bit field with a little bit of binary math that sort of tells you it's possible to have, what is that, 128 possible payload types that are identified. But simply, this is a way to identify the format of the payload. An important aspect of the payload type, it can be or may be used to dynamically change the format by the sender, maybe based on some type of network performance feedback information. Maybe we're going to drop, let's say, some resolution, or maybe we're going to drop to a lower bit rate codec based on network performance. So it can be used to dynamically change things. Well, from the standard, this is how the payload types are assigned or identified, which is simply a number from 0 to 127. And of course, this may be a little hard to see, but you know, accepted codec types are assigned this payload type. This is a shorter list that attempts at least to put some of the more popular formats together in front of you. We also have the timestamp field. The timestamp field is a 32-bit field, and it simply indicates the time relationship between the packet. The very first packet that is sampled is assigned this random number. Now, it's important to, I guess, realize and remember that the timestamp is not clock time. To me, when I see the word timestamp, I think of clock time, but in this case, it is not clock time. That timestamp increments for each RTP packet that is sent. The increment of that packet, however, is going to be different depending upon the application. As an example, many of audio codecs will use or send data in 160 byte chunks. Again, this is based upon a specific application. In this case, that application is sending data in 160 byte chunks. So the increment of that timestamp would be 160 with each RTP packet. So keep that one in mind. So again, that increment is dependent upon or based upon the application used. The sequence number is a 16-bit field that simply numbers the RTP packets. It is used really by the receiver to, one, detect a missing packet and/or realize or know that packets have been received out of order. The very first packet of an RTP session that is sent is assigned once again this random number. However, in the case of the sequence number, each RTP packet is simply incremented by 1. Now, related to RTP, there are some other protocols we need to at least mention. The first is the real-time control protocol, the real-time streaming protocol, and the precision time protocol. Again, separate protocols, but at the same time often used in conjunction with RTP, particularly the real-time control protocol. So looking at the real-time protocol, once again, defined under the same RFC as RTP, basically provides for the receiver to send periodic packets of performance information or network performance information back to the RTP sender. Now, there's no payload data or anything like that sent. There's simply performance information, and that might be the number of packets lost, maybe some jitter metrics, again, from actual performance. And in the case of, course, a small network where we have a single sender sending information to 3 receivers, each one of those receivers are going to send back RTPC packets to that sender, as you can see in the illustration. We also have the real-time streaming protocol defined under RFC 2326, and it's a application level protocol that allows the receiver to control the real-time information that is sent. And by controlling it, such things as maybe pause the playback, maybe reposition that playback. In other words, slide forward, slide backwards, maybe fast forward or rewind. Well, gosh, that sounds like something I might do with a DVD player and my remote control. Well, this was the exact idea that was utilized in the design of RTSP, was to emulate the functionality of a DVD player. And of course, if your favorite internet streaming application may just offer this type of service, but of course, not every application that uses RTP will use RTSP. In terms of looking and kind of a schematic of how it works, again, it is control information that is sent basically from that receiver back to the sender. A couple of maybe minutia to point out, but I think it's important to understand the port number. By a capital N used for the port number, that indicates that port number will always be a positive number. And with that, the RTP's control sender port is always going to be that port number +1. Thus, it's going to be always an odd port number. Port numbers are going to be assigned over a wide range of UDP port numbers, ranging from, let's say 1024 up to 50 something thousand. So again, dynamically assigned. And of course, a important aspect is the synchronization, and this is where the precision time protocol comes into play, also known as IEEE 1588, with the current version designated as 2008. You also may see this nomenclature shown as PTP v2 to indicate version 2 of PTP. But PTP is a hierarchical master-slave algorithm for time synchronized distribution. Very accurate in terms of accuracy. You can achieve sub-microsecond accuracy with PTP. Now, I had mentioned that the timestamp within the RTP header was not clock time. Okay. Obviously, PTP does provide clock time, but the clock time is not really utilized. What is utilized is the accuracy of that clock for particularly in applications where you are synchronizing multiple streams to maintain that synchronization. And probably the best way I think of that is in the case of an audio and video stream is maintaining that proper lip sync that sometimes can get out of whack. Anyway, PTP is also distributed commonly over UDP, although it can be distributed over unicast. Typically, it utilizes UDP in a multicast type environment. The clock time of PTP is based on the Unix epoch, which of course is January the 1st of 1970. We'll talk a little bit more about that. It is a hierarchical system where you have the grandmaster clock, you have the boundary clock, and then you have the ordinary clock. There is, again, this process to establish. Now, looking at clocks, of course, there are several different types of clocking or time reference systems. And of course, they all have different accuracies that they can generate. And as you can see, PTP is pretty darn accurate. Not as accurate as an atomic clock, but not practical for us to have atomic clocks in our facility. And of course, PTP generation devices are what can be, you know, that several $1,000 box maybe, but also they can be a few $100 boxes in your facility, particularly as you see the time machine time server there. But there is a algorithm or a process to exchange information between a master clock and a slave. And of course, as we had mentioned, the Unix epoch is used, and at least at 8:21 this morning, there is the time, the Unix time expressed. And you, of course, here's a reference where you can always go make that conversion back and forth between what might be real time or calendar time and Unix time. Again, from a implementation of PTP, we have this hierarchical arrangement between the grandmaster clock, the boundary clocks, and the slave clocks that are in turn slave to those boundary clocks. From a practical implementation side, this may look like something like this, where we finally get down to our individual media type devices that are connected to our network. And of course, there's a lot more to learn about PTP, and here's a URL for some further study on that particular topic. So looking kind of wrap up some closing thoughts. RTP, again, is a transport protocol for real-time media delivery. It is a foundation of our well-known audio over IP systems that are in use today. What it does, it corrects for jitter. It does not correct, it recognizes out of order packets, okay? And through buffering, allows the application to correct that. And also it detects packet loss, but it's also important to note that there's no correction offered by RTP. It's just the detection of the packet loss, and that packet lost information then in turn allows the application involved to correct or conceal that packet loss. And of course, depending on what the application is and what the payload is, that may be done in different ways. If it's a frame of video that is missing or is lost, then maybe the previous frame of video is simply used. Often in terms of missing audio, a previous good packet of audio is used for that concealment process. RTP is likely going to be used in conjunction with RTCP, the control protocol, but certainly the RT, or real-time streaming protocol, and PTP are likely going to be used as well. Keep in mind, RTP does not have any inherent QoS features or quality of service features. However, it does again provide quality of service information to the controlling application. It does not have really any error correction or concealment features within it. And also keep in mind, I think importantly, that RTP header timestamp is not clock time. It is a timestamp really that is unique to the particular payload. And for some more study, a couple of URLs. The first one is basically a chapter of a textbook which goes into extreme detail on RTP, RTCP, and RTSP. And then finally a YouTube video that's about an hour long that is focused upon ST2110 in terms of the video transport standard, but there's a good section within that video on RTP. Keep in mind what we're really trying to fix. Keep in mind that real world network environment that's got some problems. Problems often are jitter, packets out of the order, maybe packets simply missing. This is what we're trying to fix. So with that, that's about it for me. Always keep in mind there's more to networking than just hooking things up. And with that, I thank you for your time, and I welcome any questions. Either today or down the road. You'll see some contact information there for me. And with that, Larry, I'll turn it back to you and John.
Yeah, I had a couple of questions real briefly here. When packets were received out of order, you mentioned that they could be put back into order somewhat because of buffering. And I assume that buffering and all that would actually increase the latency of the audio that's coming in or the video that's coming in. Is that correct?
Yes, it would. One key thing, though, or point maybe to add is that reordering is done by the particular application involved rather than RTP doing it. It just simply is passing that information, and the application is putting that back in order. So depending on what the application is, really addresses how that might be done.
That doesn't really have anything to do with the distribution. It actually happens at the end user and how much latency they can tolerate, I suppose.
That's right. That's right. And again, different applications are used for different scenarios. If you think about, and it's probably the simplest application I think about is listening to your favorite streaming audio source. Gosh, there's already still latency well into seconds in that regard. But that is a very, very specific application. That 6 seconds of delay or latency wouldn't necessarily work so well in a let's say a audio or a audio video transport. Let's say if you were doing a live interview or something, you know, that would, so as a result, that application that you use is going to have to be a lot lower latency.
So I suppose with the live situation, you wouldn't really rely too much on reordering package or even drop-in package. You just keep on going and drop the one out that's bad.
That's right. You keep on going, and that might be one where you use the last good one you have. And of course, depending upon the numbers of think about some of the applications out in the marketplace. And of course, if it's an audio application, you hear the blips and the burps that are often, basically missing information. In video information, you see often the application downscales to a lower resolution to try to get some, frames of video through. You see things freeze, and if there's just not enough data there, the screen maybe just goes black.
I actually saw that on a webinar I watched one time when they were talking about the error correction that is especially in television with ABS-B and now with the ATSC3. And it was sort of a funny story that the guy was talking about that said the TV set has a man sitting in an office at a desk, and if there's errors, he tries to correct it with some of the error correction tools that are transmitted in the stream. And if it gets too bad, it begins to pixelize. And then if it gets so bad that he can't correct it, he just flips the switch off. It goes down to Krispy Kreme and gets a donut. He said,
No.
I can't do anymore.
That's right. You just give up. In fact, it's well, we use some live view equipment for remote video transmission, and that reaches a point when it can't decode the video. It just goes to internal color bars.
Oh yeah, that's correct. Anybody else have any questions on the call? John, any comments from you?
No, not really. It was always enjoyable to sit there, and I'll scratch my head now a little bit later and say, gosh, I'm really in the way behind. So, but certainly appreciate participating with Wayne today, and you, Larry, as well.
Yeah, okay. The one other comment, Wayne, and you might want to share your thoughts on this. There was at one time, and I guess this is what you were talking about, where people were listing if they went to a stream on their portable device and they went from a really good cell service to a not too good cell service, it would actually report back to the sender, and it would drop the rate that it was sending the data to allow him to continue listening. Is that what you were talking about?
Yes, that's where the RTP or real-time control protocol comes in, of sending that feedback information from the receiver back to the sender. Hey, we need to do something, and maybe that's where we change the coding algorithm, which can be done dynamically through that payload type, can be changed.
Right. I see Mr. Harnack with his hand up. Did you have a comment you wanted to make?
Yeah, first of all, I just want to mention that Wayne has done a fantastic job of explaining this. I learned some things that I didn't know. So Wayne, thank you so much. Also wanted to point out that, RTP is used for such a variety of services, like consumer streaming, where there is a lot of buffering. RTP is also used with audio over IP, like AES67 or Livewire or WheatNet or Dante.
Yep.
And about the buffering, that's why if you're using the low latency streams, like from Livewire, where each packet literally is 250 nanoseconds of audio. I mean, it's not much. We're doing 4,000 packets per second.
Yeah, it's very small chunks of audio.
Yeah, because that's the fastest way to get something through a network, is the smaller the chunk. And so we don't have time for buffering or reordering packets. And that's why in an AOIP environment, it's so critical that the Ethernet switches be set up according to the manufacturer's directions, so that quality of service, a type of service, and the incoming queues and the outgoing queues are adhered to. So the audio or the media is the most important thing, aside from clock. Clock is even more important. The other thing I wanted to point out is what y'all been pointing out about things changing their bit rate. There's a couple of good examples of this. One is, well, the device I have behind me here, the Telos Zip 1, that was designed to dynamically change its bit rate. But the more common way that this is done for like Netflix streaming, like especially if you start watching something that's a cartoon that has definite sharp lines in it, and for the first 10 seconds, it's a little fuzzy, and then you're on a good connection, so 10 seconds later, it clears right up. That's typically done through Apple HLS or Microsoft SureStream or MPEG Dash, which actually are doing file transfers. They're actually not using RTP. They're actually doing a TCP file transfers of little chunks of the media. And the media is encoded at several different bit rates. And so many different bit rate copies of what you want to watch are stored on the server. And indeed, in real time, if the playout device is running out of bits before the time is up, it judges based on how long does it take to download 10 seconds of video. If it takes 12 seconds, well, we got a problem. If it takes 2 seconds, well, we're doing fine. So there are more consumer-ish means that are actually pretty simple to overcome that problem. But it is interesting that, yeah, I wasn't aware of the control protocol. So that's an interesting, I figured it was in there, but I never really heard about it. So Wayne, thanks for teaching us about that in addition.
Yeah, one thing I probably should have commented on early when we were talking, particularly about the audio over IP systems, and specifically UDP as being this best effort or non-guaranteed. Really, in those type of systems, I think the key is you're relying on the pristine performance of the network. Whereas in that consumer streaming application, the public internet has its challenges, and you're compensating for that. So over in that broadcast, let's say audio over IP system, I'm relying on that pristine performance of that network, which might be as simple as specifying certain products, particularly Ethernet switches, that have the processing horsepower to handle these multiple live streams with no buffering and very, very low latency
Okay, thank you very much, Wayne. And we really enjoyed the presentation today. And if anybody has any questions for Wayne, he had his information up earlier, or you can contact me and I'll give you his contact information. Reminder, our next webinar will be actually on December the 20th, which is actually Christmas week, but we got somebody lined up, and this was the only day we could get him. Skip Peasy will be with us. Skip is a world-known guru when it comes to ATSC 3.0, and he's going to, like Wayne went through and told us all about RTP, Skip is going to tell us about ATSC 3, which is being implemented at TV stations around the country all over all over the United States right now, and in some other countries as well. So mark that date on your calendar, especially you TV guys, because Skip knows exactly how ATSC3 works and what you as a broadcast engineer need to know to implement it at your station. So with that, any more comments from you, John?
None. Just hope
Okay.
everybody has a good Thanksgiving.
All righty, same to everybody else. And so thank everybody for watching, and we'll see you on December the 20th.